Okay, good morning, everyone. So before I start, I should perhaps say I'm a bit embarrassed to say that, but that's actually my first time in Saint-Flour. So yeah, I'm not sure how it goes in terms of the level. So please don't hesitate to interrupt, to tell me, to complain that it's going too slow or too fast, and I will adapt. So today I'm going to start very slowly by recalling things that probably all of you know, but it's mostly to set up the notation. So here is the setup. So I'm going to denote by X a state space, which for me will be finite most of the time. So just makes my life simpler, but from time to time I will allow myself to consider diffusions on the Euclidean space or manifolds. And then we'll go a bit beyond that. But most of the time, my state space is finite. And I'm going to define a dynamics on this state space by just looking at a transition matrix, right? So just a stochastic matrix. Okay, so the picture that you should have in mind is the following. So you have a state space, maybe 3 states here. And this stochastic matrix just tells you, gives you numbers that indicate the probability to jump from a state to another one. So I'm sure everyone has seen this type of diagram. And I'm going to assume, so on those arrows, you get the numbers that are indicated in this stochastic matrix. And I'm going to assume that the diagram that you see here is connected, right? So in terms of matrices, just means that this is irreducible. Again, if this is not clear, please don't hesitate to ask. Okay, and the basic result in any book on Markov chains is that if you look at the dynamics that is induced by this stochastic matrix, this dynamic will converge in large times. Okay, so for me, actually, it will make my life much simpler to, instead of looking at a discrete time process, to look at the continuous time version of it, to avoid those periodicity issues that you might have with this discrete time process. So the way I'm going to do that is very simple. You just take a Poisson clock that rings at rate 1, and whenever the Poisson clock rings, you make a transition according to t. Okay. So maybe let me write it explicitly. So here is the continuous time semigroup. Associated with this matrix T. So the probability that after any time T, you find yourself at Y given that you start at X is given just by a simple formula. You count how many times your Poisson clock actually rings, and this is just a Poisson random variable. So the probability that it's equal to K is just given by this formula. And then given that your Poisson clock rings K time, you just apply K times this transition matrix. Right? So you raise T to the power K and see where this leads you. Okay, so maybe most of you are used to writing this in a exponential form, just like that. It's much simpler, where L is the generator, and for me the generator is just T minus the identity. Okay. So it's just a compact version to write what is above. Okay, so now I can state the result I was mentioning to you, the basic result about Markov chains. So if I assume that my state space is finite and my transition matrix is irreducible, then several nice things happen. The first one is that there exists a unique invariant measure for the dynamics. Right? So I'm going to denote this measure by pi. So it's a probability measure on the state space, and it is invariant when I make transitions according to t. Of course, if it's invariant under t, then it's invariant under t power k for any k, so it's also invariant under this. Okay, the second thing is that this probability measure puts a positive mass at every state on my state space. So the support of pi is actually the entire space. And this follows from this irreducibility assumption. You have a positive chance to visit everyone. And the most important statement is that this pi is a unique attractor for the dynamics. It's a global attractor for the dynamics. So you start from any initial distribution mu, and you run your dynamics for time t. So that's the distribution that you get after time t, right? Just mu times pt. And if you wait long enough, this distribution will be very close to pi. Okay. So I will not prove this theorem now. Maybe later I will give you a two-line proof of this. It's a basic result again about Markov chains. Okay, so this phenomenon here is called mixing, and the reason that it's called mixing is that you start from a particular distribution mu, but then as the dynamics evolve, you progressively forget that you started from mu, and you approach a distribution that is completely independent of your initial conditions. Right? So you can think of there are many concrete examples of this phenomenon. You can think of what happens when you shuffle a deck of cards. Right? You start from a perfectly well-ordered deck of cards, and then you repeatedly shuffle it. Progressively, the deck will forget the fact that it started from a particular state, and it will converge to the uniform distribution over all possible orderings. Right? You can also think of a gas of particles that equilibrate inside the box. Right? You start, you divide your box into two compartments. You put all the particles on one side, and then you remove the thing that is in between the compartments, and you let the particles evolve. So they will do random motions inside these two compartments, and they will equilibrate. Right? So that's also an example of this phenomenon. But you also have modern applications of this. I'm sure at least half of you are familiar with this. This theorem here is the basis behind the Monte Carlo Markov chain revolution in computational statistics. Right? And I will give you more details about this maybe tomorrow. But it's a very important application of this mixing theorem. You can also think of the Google PageRank algorithm, which is also again an application of that, and I will tell you more about this tomorrow. Okay, so this is just a motivation. If you think of all those applications that I mentioned, the crucial question, which will be the one that will occupy us for the 2 weeks, is how fast is this convergence? Right. So how long do you need to wait until this distribution is close to this one? Okay. Okay. So to answer this question, we need to agree on a way to measure the distance between this object and this one. Those are two probability measures on a finite state space. So there are many ways to define distances. I will focus on one specific, which is probably the most interesting from a probabilistic point of view, and it's total variation. Okay. So there are many equivalent formulations of this. I will try to give all the ones I know and explain why they are equivalent. So the basic definition is the following one. You take a region in your state space and you compare the probability of it under mu and the probability of it under nu and take a maximum. Okay. But of course, by changing A to A complement, this difference here is just negated. So if you want, you can just remove the absolute values. Right. And the reason I'm doing that is that then you get, so this is just because you can replace A by A complement. And now, because of this, without the absolute values, it becomes clear what A maximized is this, right? Because this is just the sum over all x in A of mu of x minus nu of x, right? And now the question is, how should you choose A to maximize this sum? Well, it's pretty clear. For every x, you want to put it in the set. If this is positive, you want to avoid it if this is negative. Right? So the correct set here, the set that maximizes this is just the set where mu is larger than nu. Right? Okay, and so from that you get this explicit expression that it's just the set, the sum over all x of the positive part of mu minus nu. Okay. Now, if you remove this positive part, this would be 0, right? Because those are probability measures. Right? So the positive part, the sum of the positive part is the same as the sum of negative part, and so it's 1/2 the absolute values. So that's another nice expression. Okay, and this is just because the total sum is 1. Okay, maybe coming back here, the a minus b plus is also a minus the minimum of a and b. And using this, you get just 1 minus this. So again, another expression for this total variation distance. We are going to use all of those formulas, so it's useful to have them for once. And now my claim, and this is probably the most useful formula for us, my claim is that this total variation distance is also can also be expressed as in terms of couplings. Right? You take a random variable with distribution mu, you take another one with distribution nu, and you look at the probability that they are different. Right? So this will depend a lot on how you choose to couple mu and nu, and you are free to do this as you want so as to minimize this. Right? So you take the minimum over all possible couplings of this. Okay, so why is it true? Well, from this formula it's quite clear because of this picture. So let me represent the state space here on this axis. And let me represent this distribution mu's and nu's like that. So this is maybe, this is nu, and this is nu. And the goal is to couple them so that you have a large chance that they agree. And it's quite clear how you can do that. The best thing you can do, on this region where you have the same mass, the common mass for both of them, you really want to put, here you can put the mass so that x is equal to y. And outside of this, you have no choice, x and y will be different. And if you look at this mass, it's precisely this. Right? Precisely this mu minimum nu. Right? So you get exactly this formula. Okay, all of those identities I'm sure you know, but it's good to write them down for at least once because we are going to move between those many times. Okay, so here is a nice fact about this total variation distance. Remember that we want to understand the total variation distance between this and this. And the nice thing is that whenever you apply your dynamics, this total variation distance can only decrease. Right? So if you look at the total variation distance starting from any measure and applying your dynamics for a time t, and compare it with the same but starting from nu, okay, you can explicitate this just using maybe this one. So it's sum over all x, and then nu ptx minus nu ptx. Okay. So this is sum over x, and then inside there is a sum over y, mu y ptyx minus mu y ptyx. Okay, and I'm going to just bring these absolute values inside the sum, so it's at most a double sum xy, and then you get just uy minus uy Ptyx. Okay, so just the triangle inequality. But now you see when you sum over all x, becomes 1, so this disappears. Right, so what you get is just this. Right? This gets removed when you sum over all x. And what you get is just the totalization distance between mu and mu. Okay, so whenever you run your dynamics, the distances become, the measures become closer and closer to each other. Okay. And in fact, this inequality is even strict, if you look at it. So there is equality only in the degenerate case. Right? So when do you have equality in the triangle inequality? Well, when all those numbers here have the same sign. But those are probability measures. So if you want this difference to have the same sign, then mu has to be equal to nu. Implicitly here, I'm using the fact that this is strictly positive, right? And this requires t to be non-zero. Okay, so really this distance is decreasing. I mean, the measures become strictly closer to each other when you run your dynamics until they become equal. Okay, so now comes the main definition. So the distance to equilibrium at time t for my Markov process is this. I'm going to simply take the total variation distance between the law of my distribution at time t, right, the law of my chain at time t, and the equilibrium measure. And then I take a maximum over all mu, a supremum over all mu. Okay, so when this quantity is small, it really means that your Markov chain, your Markov process is close to equilibrium regardless of the initial condition that you chose. Okay, it's uniform in this. But if you look at this definition, maybe this one is simpler. This total variation distance, you see, it's a maximum of linear functions of mu and nu. So it's convex in mu and nu. And so this supremum is actually just, by convexity, it's achieved at Dirac masses. So it's just a maximum over all possible initial states. And then you look at the dynamics starting from this state. Right? Okay, so instead of considering the worst case initial distribution, it's enough to consider the worst case initial state and start from there. Okay, just by convexity. So this is convexity of this total variation distance. Okay, so let me draw a picture of this function of time. Here is how it looks like. So this is time. And this is your distance. So total variation is always between 0 and 1. In this case, it starts very close to 1. And then it's always strictly decreasing, and it's decreasing to 0. Typically like that. Okay, so remember we had this question, how fast does this convergence to equilibrium occurs? Now that we have formalized things a bit, the question becomes, what's the time scale on which this function goes from 1 to 0? Okay. Okay, so to answer this question, what's the time scale on which this function goes from 1 to 0? There are actually two answers to this question. So this defines two different times. One is the relaxation time, and the other one is the mixing time. Okay, so let me start with this very important property of this distance. So I told you that it was decreasing, strictly decreasing in time from 1 to 0. But in fact, it's roughly an exponential function in the following sense. That it's submultiplicative. So if you look at the distance to equilibrium at time t plus s, it's at most distance to equilibrium at time t times the distance to equilibrium at time s. So that would be exactly submultiplicativity. It turns out that this is not quite true. You lose a bit here. Just have a 2. But it's not a big deal. It's important that it's there, but in terms of the consequences, you will see it's not a big deal. Okay, so if you think of a function like that, forget about the 2 and maybe put an equality here. This really means that your function is an exponential, a decreasing exponential. Right? So that's what this lemma says, is that not only the convergence, this converges to the equilibrium, but it does so in an exponential way. Okay, so let me prove this. Okay, and I'm going to, those type of things, we'll see this a lot. It's usually the case that on Markov processes that if you look at the quantity at time t plus s, it's related to the quantity at time t and the same quantity at time s. And that comes from the semi-group property, right? Which is clear from this exponential notation that you have this. It's called the semi-group property, right? And this implies a lot of formulas like that. Okay, so this proof will be an example of this. Okay, so the way I'm going to prove this inequality is using this formulation with couplings. So I want to couple a Markov chain starting from x. Okay, so fix an initial state. Let me denote it by O. It's my origin. And then I'm going to construct a coupling of the Markov chain at time t plus s starting from this and the stationary measure. Okay, so by a coupling, I simply mean a pair of random variables like that, where one has one distribution and the other one has the other distribution. So I'm going to construct a coupling x prime, y prime. Right? I want to understand this, so I'm going to consider a coupling between law of the Markov chain starting from O at time t plus s and the stationary measure pi. Okay. So here is my coupling. I'm going to use this Markov property to, instead of running directly my Markov chain for time t plus s, I'm going to run it for time t and then for time s. And so I'm constructing this coupling in 2 stages. I first generate a random pair xy. According to an optimal coupling. Right, optimal means that you have equality here, right? One that achieves this minimum. Right, so I'm taking an optimal coupling for time t, and then given where I arrive, so given that xy is any possible realization that you may look at, I'm going to generate x prime and y prime. According to an optimal coupling of the dynamic at time run for time s, starting from x and starting from y. Okay, so I'm really doing this in 2 stages. I first run the dynamic for time t, look at where I arrived, and then generate another coupling for a time s. Right? Yes? Optimal means one that achieves this minimum here. Okay? Yes, yes, yes. So this is a special case of optimal transport for a very stupid distance, which is the trivial distance. We'll see this later in a bit more generality. But so far, don't think about optimal transport. It's just, this is a nice, the set of couplings is compact, so this minimum, this infimum is always achieved. Okay. We'll see this in more generality. But. Okay, so the first thing I claim is that x prime, y prime is indeed a coupling of this. And that's really just this property, because I'm looking at x as this distribution pt, and then I'm running ps starting from that. So in the end, I get pt plus s. And for the other side, y as distribution pi, and then starting from, given where I am, I'm applying ps again, but pi is stationary. So what I get in the end is pi. Okay, so this is a coupling. And because it's a coupling, I have this inequality here. Okay. If I want to estimate this total variation distance, it's a minimum over all possible couplings. Here I have one particular coupling, so it's certainly at most the probability of this. And now I'm going to compute this. Okay? So again, this inequality would be true for any coupling of those 2 distributions. Here I have chosen a specific coupling so that I can evaluate this and get what I want. Okay, so let me evaluate that. This x prime, y prime was generated in 2 stages, so I'm going to compute this probability in 2 stages. Right? I'm going to sum over all possible realization for the first stage. Right? And then given that I see x and y for the first stage, I'm going to look at the this probability given this. Okay. Okay, so maybe this optimality, given the realization of x and y, x prime, y prime is generating as an optimal coupling. So this means that this is exactly the total variation distance between ps x and ps y. Okay? And in particular, by the triangle inequality, this is at most twice the distance between one of them and pi. And so it's at most twice this maximum function, this dtvs. Okay? So that's a trivial bound. I'm going to improve it just a bit by saying that if x is equal to y, then this is actually 0. So I can also put this. Yes, this total variation distance at time s. S. Okay. Just the triangle inequality. Right? I want to compare this one to this one. And instead, I'm comparing each of them to pi. Okay, so now what I get when I replace, when I use this inequality is this. And now I'm summing over all x and y, but now I have this indicator that tells me that they are different. And this is probability that x is equal to x and y is equal to y. Right? So that's what I get when I replace this by this. Okay, but this is exactly the probability that x is not equal to y. And if you look at how I decided to couple the first stage, for the first stage, this was an optimal coupling. Right? So this probability here is exactly the total variation distance between this and pi. Okay? So you see that in the end, you get this. Okay? So my inequality is that the distance to equilibrium at time t plus s starting from any state is at most this, and then I take a maximum over all possible initial states, and I get the result. Okay, so why is it important to have this property? I told you that roughly this means that the distance to equilibrium decays exponentially. Well, let me maybe remind you a simple exercise that I'm sure all of you know. So let f be a function, any function on the real numbers, maybe measurable, which is subadditive. Subadditive means that ft plus s is at most ft times fs, plus fs. Then I can conclude from this that ft divided by t converges. And I even know what the limit is. Then the limit as t tends to infinity of ft divided by t exists, and it's equal to the infimum over all t positive of ft over t. Do you know this lemma, subadditive lemma? It's an easy exercise. It's often called Fekette's lemma. Okay. So I leave the proof to you, and then we apply this to a particular subadditive function, which is given by this this lemma here. So this is submultiplicative, not subadditive, but it's okay. You take a log, and it's there is this annoying 2 factor. So it's not really subadditive when you take the log, but if you really want, you can just put a 2 here, and then put a 2 here. And then this is a submultiplicative function. Okay. So what I'm saying is that the log of 2 times dtv of t, this is a subadditive function in this sense. Okay? And so what I get is this nice corollary, that there exists a number, lambda, which is actually strictly positive, which has 2 properties. The first one is that this distance to equilibrium dtv of t, when t is large, is roughly exponential, an exponential decay, a decaying function like an exponential, okay, up to some error term, which is little o of t. Okay, so I told you that this means that it's roughly exponential. Here is a formalization of that. And again, this is just saying you take log, and you are just saying that, yes, it's exactly this exercise here. Okay. The fact that this is strictly positive simply comes from the fact that the limit here is the infimum. And the infimum of, I mean, we know that this quantity here will tend to, so this will tend to 0, so this will tend to minus infinity. So we know that it will be negative at some point, and that's where this comes from. Okay. And the second thing, which comes from this characterization of the limit, is that you actually, so this is asymptotic. This is only as t tends to infinity, but there is a statement that works for every t, which is this inequality. It's always at least exponential of minus lambda t exactly. You just have this annoying factor 2. Okay. So this is not asymptotic. This is for every t. Okay? Yes? Yes? So, okay, maybe the proper way to say it is that conditionally on the random pair xy, the distribution of x prime y prime is an optimal coupling of ps capital X, ps capital Y. But this is what it means. Right? Instead of specifying the distribution of x prime y prime, I'm telling you the conditional distribution of it given this for every possible realization. So then you know everything. Okay. Maybe an important remark is that this lambda here, it's not very very explicit in this corollary, right? You give me any Markov chain, and there is it tends to equilibrium at an exponential rate, lambda, but you don't know what this lambda is. Okay. In fact, there is a nice characterization of lambda if you know the eigenvalues of your matrix. I'm not going to prove it, but it's an important remark. You can relate it to the eigenvalues of t, so it's exactly the difference between the two largest eigenvalues of t. Your transition matrix T, except that, you know, we did not make any assumption on T in terms of reversibility or, right? So it's not clear that the eigenvalues are even real, they could be complex. So you need to project once projected on the real axis. Okay, so maybe let me draw a picture. Like the eigenvalues of a transition matrix, one is always an eigenvalue. But the other one could be complex. They could be anywhere inside this disk of radius 1. And what I look at, so this lambda here on my picture, right? So you have a lot of eigenvalues like in this disk. But lambda is just, you take the projection, and this is lambda. Okay. So because it's a difference of eigenvalues, it's called a gap, the spectral gap. Okay, it's a name that I'm sure you have heard, and that's where it comes from. No, between the two largest. So the largest is always 1, in fact. And you look at 1 minus the closest to 1 once projected here. Right? Okay, so that's a nice spectral interpretation of this parameter. And the proof of this is easy if T is diagonalizable. And then you can argue that, even if T is not diagonalizable, you can at least re-diagonalize it or put it in Jordan's form, and then you get this easily. We are not going to use it, but just wanting to mention that. Okay. So what is this corollary saying here? If you believe in this approximation that this is roughly an exponential, right? Then you remember the question was, what's the time scale on which this function goes from 1 to 0? Well, if this behaves like that, then the time scale that you want to look at is 1 over lambda. Okay, that's the answer. Okay, so that's my first interesting time for the dynamics. It's 1 over lambda. The time scale on which this exponential decays from 1 to 0. Okay, so definition. It's called the relaxation time of the system. I will explain the name later. So it's denoted TREL for relaxation, and it's simply 1 over lambda. Okay, and again, it's the time scale on which this function decreases by a factor 1 over e. Okay, and because of this spectral interpretation, there are many tools to estimate the spectral gap of a Markov chain. So because of this, it seems that we have sort of completely answered our question. What's the time scale on which I have to wait before being close to equilibrium? Well, 1 over the spectral gap, and then I have a rich set of tools to estimate this on practical models. So that's it, right? End of the course. Right? Of course, this is not true, and the reason is that this approximation here, there is this asymptotic here. This is only true when t is larger, very large compared to 1. Okay? So this means that this nice exponential behavior is actually describing not this entire curve, but roughly just what happens somewhere here. Right? So if you zoom here on this part of the picture, what you'll see is a nice exponential, and indeed on this, when you zoom in, the time scale on which things decay here is really 1 over lambda, so the relaxation time. Right? But this approximation is valid only when t is large, so it doesn't tell you anything about this, right? Right? And when you run your dynamics, think of shuffling a deck of cards, right? You are really starting from the worst possible initial condition, and the question is, how long do you need to wait before your distance to equilibrium becomes so small that this exponential behavior starts to be valid. Okay? And so this quantity is really what you want to understand. It has nothing to do with this TREL. Okay?
So here we draw a convex function. Do we know it is convex?
No, it's not convex. It's important that it's not. Yeah, good question. You'll see later. Today, actually, you'll see that it's very, it's in general not convex. Okay, but there are cases where it really looks like that, but there are cases where it really looks like something non-convex. Okay, so the main question in practice, if you do Monte Carlo Markov chain simulation, for example, is really this quantity here, not this one. So why is this called the relaxation time? Well, in physics, relaxation is what happens when you are at equilibrium. You make a very small perturbation, and you wait until your system goes back to equilibrium. Okay? So that's exactly what this picture tells you, right? TREL, this relaxation time, is the time on which you converge to equilibrium when you are already very close to equilibrium. Okay. Once again, this is not the quantity we are interested in. We want to understand this one. So here is the definition that really capture what I want to understand in my Markov chain. Right? Remember, there are two different time scales: this relaxation time, and now the mixing time. And the definition of this mixing time is exactly this. Right? So this is T mixed. Right? So how would I define this? It's the time at which your distance to equilibrium becomes small. Okay. So I'm going to take a threshold, say epsilon, and look at when my distance drops below this, and this will be my mixing time. And think of epsilon being small. Okay. So we have seen that this distance to equilibrium is a nice, strictly decreasing function. It's continuous. So there is a time at which this distribution will reach, this distance will reach epsilon. I'm just going to look at this time. So it's the inverse evaluated at epsilon, or if you prefer, it's just the minimum t, such that at this time, I'm less than epsilon. Okay, and epsilon is a fixed precision, which is just the precision that you want to reach. Okay. So if you want to do Markov chain simulation, you have a certain error that you are ready to allow. Right? You want to produce samples from a target distribution pi. You are going to do that by running your Markov chain, and you allow yourself a certain error in total variation distance. That's your precision. If you want to play cards, right, you are going to shuffle the deck of cards. It will never be perfectly uniform, but you allow yourself a certain precision, and you shuffle your deck of cards until you reach this precision. So epsilon depends on your particular model. And that's the parameter you want to understand. Okay. Maybe an important remark, which makes sense, right? So this is time to converge to equilibrium when you are already very close to it. This is time to converge to equilibrium when you start from very far away. So of course there is a relation between the two. The time to converge when you start from very far away is of course larger than starting close to equilibrium. And the correct formulation is this. Okay. And the proof is just this. Right? We know that this is larger than this. Right? So if you want this to be equal to epsilon, so take t equal t mix of epsilon, and then you know that this is equal to epsilon, so you get, which is the same as saying that t is larger than this. Okay. And as you will see in many models, it's the case that this is actually much larger than this. Okay, so the time to converge to equilibrium from the worst case initialization is usually much, you have to wait much longer than starting very close to equilibrium, which makes sense. Okay. So this mixing time is the main parameter that people study in the community of mixing times. There are now a very well developed set of tools to analyze mixing time. And the interest usually is what happens when the state space becomes large. Right? You want to understand, you think of your deck of cards or a big gas of particles or your Monte Carlo Markov chain simulation. Usually the state space is huge. Right? And so you want to understand these mixing times, how it will scale as the size of your system goes to infinity. Right? So you want to understand large scale asymptotics. Which means that your state space is really large. Right? You should think of the number of states as going to infinity. So the way to formalize this is that I told you at the beginning that my main ingredient was a transition matrix. But instead, I will always assume that instead of having a fixed transition matrix, I have an entire model, which means the sequence of transition matrices is indexed by a parameter n, and n represents the size of the state space, and n tends to infinity. You think of all the examples I gave you, there is always this parameter. Right? If you shuffle a deck of cards, then there is an n, which is the number of cards. If you look at a gas of particles in a box, n is the number of particles. Right? There is always a size parameter in your model, and implicitly you think of this size parameter as being large. Okay? So we'll consider a model. And for me, a model is just a sequence of transition matrices. And each of them is defined on its particular state space, so you have a sequence of state spaces. Okay, so that's what a model is. It's not a fixed Markov chain, it's a sequence of Markov chains. Or you can think of it as just a Markov chain, but indexed by n, a size parameter n, and you can vary n. And what you really want to understand is what happens when n tends to infinity. So I will write things like, instead of having T mix of epsilon, I will have T mix of epsilon, but for my, depending on my size parameter n. And the question is, how does this behave as n tends to infinity? Okay? Yes?
So implicitly, we assume that xn go bigger and bigger.
No, I mean, yeah, that's what you should think of. I mean, in all the examples that you think of, whenever you do, actually, in every probabilistic model that you look at, there is always a size parameter. Right? But for my definition here, it's totally general. You could think of those are being completely unrelated to each other. Right? You don't need xn to sit inside xn plus 1 or anything like that. You don't even need xn to the size of xn to tend to infinity. Okay, but of course, that's what you have in mind in practice. Think of your favorite model, and it's clear what this xn is. Okay. I will give many examples tomorrow of models that people care about, and there you will see that there is a natural size parameter. One important comment is that, to avoid, to keep my notation simple, many times I will forget this n. I will not write it explicitly. But remember that everything depends on n, and that what ultimately matters is what happens when n tends to infinity. Okay. It's just a nightmare to keep track of this dependency in n everywhere, so I will simply remove it. Okay, so maybe just to address this precision parameter epsilon, it's a bit annoying to have a mixing time that depends on epsilon, but an important fact is that this epsilon does not really matter. So there is a default parameter for mathematicians. I told you this epsilon depends on your application. For mathematicians, epsilon is 1 over 2e. That's the precision that we care about. Of course, Monte Carlo Markov chain, in Monte Carlo Markov chain simulation, people will tell you that this is very bad. This is a terrible precision. You really want much more. But then the mathematician will argue that if you want much more, then really, so usually we take this and we write simply, you drop the epsilon in the notation, so you simply write T mix for T mix of 1 over e. And it's always nice, 1 over 2e. It's always nice because then you have a parameter that does not depend on anything. This T mix is really a quantity that is associated to your Markov chain, no parameter in it. It's one single time, right? And the point is that this T mix, this precision 1 over 2e is enough to capture every other precision that you want. So for any precision, if you want something better than this, And again, think of the people working in Monte Carlo Markov chain. They really want epsilon to be much smaller. But in fact, if you want to understand T mix of epsilon for a precision that is much better than 1/2e, certainly you will have to weight more than T mix for the mathematician, right? Because your precision is better, so you have to weight more. But you don't have to weight much more. Maybe with a 2. Okay? So my claim is that up to this universal constant here, T mix of epsilon is the same as T mix. The only thing that will change if you change the precision is the prefactor. Right? Remember that everything is going to infinity, n is going to infinity. What you want to understand is how this mixing time scales, like is it n squared, exponential of n, log of n. So you really don't care about this prefactor. Right? So in terms of asymptotics, or at least order of magnitude, the precision epsilon does not matter. It only affects the constant in front of the mixing time. Okay? So this is trivial, this is by monotonicity. This follows from this sub-multiplicativity lemma. Right? You know that if you wait for this time, then your distance to equilibrium will drop by a factor 1/e. Each time you wait for this time, you drop by a factor 1/e. So if you wait for a multiple of this time, then you decay by a exponential of -k, where k is the multiple in front. Right? So it's just a consequence of sub-multiplicativity. So this is just TV t plus s, or TV k times s, is at most, maybe. Times dTvs times 2. Okay. Okay, so let me now give you examples just to understand what those mixing times and relaxation times look like on toy models. Okay, just for concreteness. So those examples are not interesting from the point of view of applications, and tomorrow I will introduce many much more sophisticated and interesting models. But the nice thing with those models is that you can compute everything, right? So it's good for, to get used to those notions of mixing time. It's good to look at what happened in this case. And those toy models, we'll take them as references for many things, so it's important to understand what happens there. So the simple Markov chain I can think of is just random walk on a cycle. So that's my first model. The n cycle. So what is that? So you look at the discrete cycle of length n, right? And you put a dynamic on that, the simplest dynamic you can think of. So whenever you are in a state, say this one, and your Poisson clock rings, you just move clockwise or counterclockwise with equal probability. Okay, that's the simplest dynamics you can think of, maybe. And you see here there is a natural size parameter. It's just the number of states in your cycle. So that's really a model. It's not a fixed Markov chain. It's a model that depends on it. Okay, so more formally maybe, the state space is just the set of integers mod n, and your transition matrix is mostly 0. The only non-zero entries are when you are neighbors. So it's 1/2 if y is x plus or minus 1, and it's 0 else. Okay? Very simple Markov chain. What's the stationary measure for that? Uniform. By symmetry, every state looks the same. Right? So that's, okay, because of symmetry, and we'll see tomorrow how to formalize this in a more general setup, but this chain is clearly symmetric in the sense that every state plays the same role. So pi is uniform. And also, remember in my definition of the total variation distance, there is a maximum over all possible initial states. in this case, it does not depend where you start from. Right? The chain looks the same starting from 0 or from anything. Right? So if I want, I can choose my initial condition x0 to just be 0. Okay, without loss of generality, because the chain looks the same starting from 0 or from anywhere else. Okay, so the question is, start from 0, run this simple dynamic, so simple random walk on the cycle. How long do you need to wait before your random walk is at a position which is roughly uniform on this cycle? Do you have any guess? So remember, everything depends on n. How does it scale as n tends to infinity? Huh? Almost what? Almost immediately? No. No, it takes quite a long time. If you start from 0, leave the room for a while, go get a coffee and come back. If you drink your coffee fast enough, your chain is very likely to be very close to this part here. So very not uniform. It will stay close to 0 for quite a while. Right? The time it takes to actually reach this is at least n, but in fact, in probability, it's much more than n. What's the typical time it takes for your random walk to move from 0 to the other side, say? Not n log n. If you look at this process from far away, it's a Brownian motion. What time? How long do you need to wait for a Brownian motion to be at? So maybe what is the distance to the origin at time t for Brownian motion roughly? Square root of t. So if you want to be at distance n, you need to wait n squared. Okay, of course that's not at all a proof. So let's try to prove this. Okay, so I told you that without loss of generality, the initial condition is 0. And I told you that this model is nice because the distribution is explicit, right? If you start from 0, then you have an explicit distribution of the description of the distribution of your chain at any time t. So in distribution, if you want to know where you are, you just need to count how many times your Poisson clock rings going backward and how many times it rings going forward. Right? So both of them are just Poisson random variable. Right? The number of clock rings for going clockwise is t over 2 after time t. And then for backward is the same t over 2, but an independent Poisson. Right? So those two variables are of course independent. Right? Just you need to remember that you are on a cycle, so you take this difference, but you take it mod n. So that's an exact description of the distribution of your system at any time t. Right? So that's what is specific to this model. When you think of sophisticated Monte Carlo Markov chain or interacting particle systems, there is no way you can get such an explicit simple distribution for any time t. Right? But here you can. It's pretty explicit. It's just a difference of two independent Poissons. Okay. So in particular, you can now see the Brownian motion picture arising here, because if t is large, this is roughly a Gaussian with mean 0 and variance t. This is just the CLT, if t is large. Right? And if you want this to be on the same scale as n, you need to take t to be n squared. Right? So that's where the intuition comes from. But still, it's not a proof of this guess here. So let's try to formalize this CLT. So the CLT will tell you that if you want to understand the position of your random walk, remember everything depends on n. And if you look at times of order n squared, so time is t times n squared, the probability that this random variable is inside any interval, say nu, nv, this is well approximated by the CLT, right? You just divide everything by n and you apply the CLT, and you'll see that this is just really the CLT. will tend to, as n tends to infinity, to just the probability that a Gaussian, that this, let me write it like that. So a Gaussian variable with parameter 0t. So this is not a very very legitimate notation, but you see what I mean. That this mod 1, because this was mod n, but I divided everything by n to get this, is in the interval uv. Okay, that's really what the CLT gives you. Okay, so in other words, you have this. Or maybe I can just explicitate this. You can write it. It's Brownian. It's a Gaussian variable. So you can write it as an integral. This has a density. You can write it as the integral from u to v of a certain density ft of z dz. And what is ft is just the density of a Gaussian with variance t mod 1. So take a Gaussian variable, take it mod 1. This has a density with respect to Lebesgue measure, and that's ft. Okay, so it looks like a complicated function, but it's just a Gaussian density, right? So it's completely explicit, ft of z. Right? It's just 1 over square root of 2 pi, that's the Gaussian density, an exponential of minus z square over 2, and then square root of 2 pi. So that would be the usual Gaussian density, but here you are folding it around the cycle, so you are taking it, so there is a t, and there is a t, and here you are folding this, taking this mod 1, so you just need to sum over the all possible number of terms that you actually make, and you subtract. So it's completely explicit. Okay, so we want to compare this distribution at time tn square to the uniform distribution. For the uniform distribution, if this was exactly uniform, then instead of having this density, you would get 1. Right? So you would like to say that the distance to equilibrium is roughly the difference between this density and 1. Okay, but here is a problem. So okay, maybe this tells you that you want to compare this to the stationary measure of the same set. And this tells you that this is roughly, as n tends to infinity, roughly this integral ft of z minus 1 dz. Okay, it's an explicit description of the difference between the distribution at time tn square and the uniform measure. Okay, as n tends to infinity. But this, unfortunately, is not sufficient at all to give you the total variation distance. Right? It's nice to be able to compare this to this, but in the definition of total variation, it's a maximum over all possible regions A in your state space, and not just macroscopic interval. Right? You would like to have here any set A, and here any set A, in particular singletons, for example. And here you only get this nice description for macroscopic intervals. The CLT will never give you more than that. Okay, so that's not enough. Okay, again, this is a maximum over all possible set A of this difference. Right? And here we just get for specific sets A, which are macroscopic intervals. Okay. The reason I'm mentioning this is that many people care about mixing times for interacting particle systems, And usually this CLT picture for interacting particle systems become just scaling limits. You have hydrodynamic limits or scaling limits for your model. It's nice, but it's just a CLT, so it will just tell you the probability that your system is in a certain macroscopic region of your state space, and this is not at all enough. This is not fine enough to understand total variation. Okay, so you need much more. Okay, so fortunately, this example is so simple that you have much more. Instead of the CLT, you have the local CLT. Right? It's a much stronger version of this CLT. Right? So it's a strengthening of this, and this tells you that the probability to find your system, not in a macroscopic interval, but precisely at a particular point on your cycle, so integer part of nz for any fixed z, that this will be equivalent as n tends to infinity to ft of z divided by n. Right? So it's a very strong form of this CLT. It implies this because you can integrate this over all z in the interval uv, and then you will get this formula. But now this is local. This tells you the probability to be precisely at a point on your cycle. Okay, so it's a much stronger thing. It's true here, just easily by Fourier analysis.
Equivalent, you mean?
Yes, equivalent means yes. Maybe I should say that. So this notation for me means that the ratio tends to 1. So n times this probability converges to ft of z. Okay, so again, by integrating this, you get this CLT. But now this is powerful enough to get the estimate that we want.
Is it uniform in Z?
You don't need uniformity. Yeah. It turns out that it is uniform, but you don't need it. So let me convince you that you don't need uniformity. So remember, we want to compute this. And in our case, it's just the sum over all x in your state space of probability that xt is equal to x minus pi of x. I'm going to use this. We saw many equivalent expressions for total variation. I'm going to use the one where you have a positive part. Okay, so that was one of the general. This has nothing to do with the random walk on the cycle. It's the general formula for total variation distance that we have seen. Okay, and because I am on the cycle, I can write it like that. It's really an integral. This sum is just an integral from 0 to n. And then I take integer part. Right? So it's pi of integer part of z minus or of x minus probability that xt is equal to integer part positive part dx. Right? It's a weird way to write this sum as an integral, but in fact this integral, this is constant from 0 to n. I was summing, the state space here is the cycle from 0 to n. So we get this. And now I'm going to do a change of variable and write it in terms of 0 to 1. Okay, so it's just n times, just by a change of variable, it's n times the integral from 0 to 1. And then I have stationary measure for x over n, for nx, sorry, or nz, minus probability nz, positive part of this, dz. Right, so far it's just equalities. Remember that this is the uniform measure, so n times this is just 1. we get just integral from 0 to 1 of 1 minus n times the probability that xt is equal to a particular position, positive part dz. Okay, so this is true for any time t. I can in particular take t to be t times n squared and use this formula here. Everything depends on n, and I'm going to look at times of order n squared times t. And I get this expression, it's integral from 0 to 1 of 1 minus n times probability that this is equal to nz, positive part d. Okay, and now I want to take t to take n to infinity. And we know by just this statement here that this will converge as n tends to infinity to just 1 minus ft of z. Right? And the nice thing with taking this positive part is that this is always at most 1. Right? So you have dominated convergence. So we can exchange limits and integrals. And you know that this, so just by dominated convergence, this as n tends to infinity will simply tend to integral from 0 to 1 of this. Okay? So you see the CLT gives you an approximation for total variation distance. Okay, so let me conclude. So if you want to understand this graph here, for random walk on the cycle, what this looks like, you need to zoom to take times of order n squared, and then the graph that you see on this time scale will converge as n tends to infinity to a limiting graph, a limiting function f of t. In fact, the convergence is even uniform because those are monotone function and the limit is continuous. So it's a uniform convergence, but we won't need that. So this means that this picture here, as n tends to infinity, converges once rescaled by n squared to a limit, and this limit is completely explicit. It's just, I can write it in a better form. Remember, this is a density, so the positive part is the same as the negative part, so I can put 1/2 absolute values. Minus 1 dz. Okay? Now this function, remember ft is sort of explicit here, so you can explicitate this, you can write it in terms of series like that. And you will see that this function is a very smooth function. It starts actually at 1, and it decays very smoothly, very continuously from, actually it's infinitely differentiable, from 1 to 0. Okay? So what does it mean in terms of mixing times? So this, remember, mixing time is just the inverse of this function. Right? So what it means is that if you want to know the mixing time, it's really of order n squared, and this is what we guessed from the beginning. And then there is a prefactor, and the prefactor is, depends on the precision that you want to reach. So you take a precision epsilon and you see how your limiting graph, when your limiting function f of t drops below epsilon, and this will be your constant here. Okay, and this is an exact asymptotic as n tends to infinity.
The function is invertible in this case.
Yes, just because it's, I told you it's very smooth, it's infinitely differentiable decreasing function. There is no problem of, yes. Okay, so we anticipated that the mixing time was roughly of order n squared. This formula tells you exactly how long you need to wait in order to get any particular precision epsilon. And again, if you look at this function from very far away, what you see is simply this nice smooth decaying function. Okay. Okay. So that's a model where you can compute everything. Okay, so here is a nice remark. Is that this random walk on the cycle is a very nice Markov chain. We can compute all the eigenvalues and all the eigenvectors. Right, you have the discrete Laplacian on the cycle, so you can do basic Fourier analysis, and you'll get that those are exactly cosine of 2 pi k over n for k between 0 and n. Okay, so you have n eigenvalues, you have n states, you have n eigenvalues, which are those ones. So those eigenvalues are like that. Right? So you divide your cycle into n parts, and then you project. Those are the eigenvalues that you see. Those are those numbers cosine of 2 pi k over n when k varies from. So what is the spectral gap? What is lambda here? It's 1 minus the closest of this. So 1 corresponds to k equals 0. And then the next one, the closest to 1, is when you take k is equal to 1 or minus 1. And so what you get is 1 minus cosine of 2 pi over n. Okay, your spectral gap is this, which behaves as n tends to infinity. Like pi square over, so 2 pi square over n square, I guess. Okay, so it means that your relaxation time, remember we have those two time scales, the time to reach equilibrium when you start from very far away and the time to reach equilibrium when you start very close. And Tyrrell, remember, is 1 over lambda. So it scales as n tends to infinity like n square. It's just n square over 2 pi square. So in this case, you see the relaxation time is of the same order as the mixing time. So it doesn't take you longer to mix starting from very close to equilibrium than starting from very far away, which is very counterintuitive. But that's the case for this cycle. You will see that this is an important phenomenon for us. Okay. So maybe as in the last minute, just as a teaser for what we are going to see tomorrow. So for the cycle, you see this nice decay. So tomorrow I will show you another toy model where this curve doesn't look at all like that. So I will give you a model where you can compute everything. It's also simple random walk on a nice graph. But then the picture that you get is this. Okay? Okay, so instead of being n square, you'll see it's sort of n log n over 4 or something. This point here. So what this means is that you run your Markov chain for a very long time, and the distance to equilibrium stays roughly the same as what it was initially, so it's 1. 1 means that you are as far as possible from equilibrium. Right? Actually, total variation distance between two measures being exactly 1 means that the measure lives on disjoint sets. Right? So you are as far as you can be from equilibrium, and you run your dynamics, nothing's happened. And then suddenly your time reaches this particular threshold n log n over 4, and then boom, you are at equilibrium. Okay, so it's not at all like the nice profile that we have seen there. Right? It's a phase transition in the way in which you converge to equilibrium. And of course, if you do Monte Carlo Markov chain simulations, and something like that occurs, you really want to know that it occurs and where it occurs, because you don't want to stop just before. And you also don't want to continue running your algorithm after. Right? It's useless. Right? So that's a phase transition, and the entire course will be to understand this phase transition. So here is an example where this phase transition does not occur. Okay.
Is this related to the cutoff phenomenon when we shuffle cards?
Yes, that's so when you shuffle a deck of cards, this phenomenon happens. So you start shuffling your deck of cards and nothing happens. You are as far as you can be from equilibrium until you have reached your deck 8 or 9 times, and then boom. Okay, so we'll see that tomorrow, and the rest of the course will be about this. Okay. So time for a break.